Thanks. So first, I want to thank the organizers for this really interesting conference and inviting me to speak. Should I talk louder? Near the mic? Okay. Okay. Yeah, so thanks to the organizers again for this great conference and for inviting me to speak. Today I'll be talking about this work with my collaborators at Princeton, Simone, Igor, Andre, and Zemo. And there'll be a lot of connections to Andre and Zemo's and Yuan's talk earlier in the conference. So I know a lot of people in this room have spent a lot of time thinking about the sphere free energy, but I wanted to start with a review, so it might be a little basic in the beginning. Starting from the very basics, if we have a Euclidean CFT in flat space, we can do a Weil transformation and put it on a sphere of radius r. And just for concreteness, here's some conventions. And the sphere free energy is defined as just the negative log of the partition function on the sphere. And the sphere radius r is an IR regulator, but we still have UV divergences here. So the general dependence of the sphere free energy on the radius and on the UV scale, which I'm calling little l, takes this form where we start with some r over l to the d, and then we go down in powers of 2. So in even dimensions, we can have a log term. And the UV divergences that have powers of 1 over L can be removed by local curvature counterterms, the schematic form of powers of the Ricci scalar. But the coefficients of log R in even dimensions and of the order 1 term in odd dimensions can't be removed by local counterterms, and they're physical. So in even dimensions, we know that the coefficient of log R comes from the Weil anomaly. So yeah. As everyone knows, if we have our CFT on a curved background, its trace is related to, on a conformally flat geometry, the Euler density times some coefficient. And then remembering that when we rescale our partition function, we pick up a factor of this stress tensor trace. You see that the free energy coefficient is just exactly the same coefficient, which I'm calling here A. So in odd dimensions, there's no Weil anomaly, but the constant term of the free energy is still a non-local term characterizing the CFT, or it's a non-local term characterizing the CFT. And in dimensional continuation, this quantity f tilde, which is the sine of pi d over 2 times the log of partition function, smoothly interpolates between the Weil anomaly coefficient in even dimensions and this order 1 term in odd dimensions. So yeah, in even dimensions, there's a 1 over epsilon pole. In dimensional continuation, that the sine pi d over 2 factor cancels. And this is from Simone and Igor in 2014 or 16. So famously, the sphere free energy obeys monotonicity theorems under the normalization group flow from UV to IR. And they can be captured by this generalized F theorem in terms of F tilde that I defined in the previous slide. Okay.
Oh, sorry. You can wait. Yeah,
Okay.
should be good.
So yeah, here are some low dimensional examples, which everyone's probably familiar with. And therefore, this monotonicity indicates that the sphere free energy provides a useful measure of degrees of freedom in a CFT, and also it can be rephrased in terms of entanglement entropy across an SQ minus 2. So as a comment, these RG inequalities are generally only true for unitary theories. And we'll be considering some non-unitary theories in this talk. Okay. So now, how do we compute the sphere free energy? Starting from the basics, for a conformally coupled scalar, the free energy is just this functional determinant of the kinetic operator, where here we've included a conformal coupling as usual. And for F tilde, this quantity is just given by an integral where we've again multiplied through by sine pi d over 2. Okay, so for some supersymmetric CFTs, going beyond the free case, for some supersymmetric CFTs, we can compute this exactly with localization. So there's see particular Sylvia's chapter in this review. But otherwise, we need to resort to using perturbation theory. So we can use dimensional continuation or the 1 over n expansion. And there's been a lot of work, especially by Lin Fei, Simone, Igor, and Grisha, that reference includes many papers. Okay, so recently also we have this new tool of the fuzzy sphere. And the connection with the entanglement entropy across the NS2 was applied to calculate the free energy for the 3D Ising model using the fuzzy sphere. And the result agreed well with what Igor and Grisha and Lynn and Simone found in dimensional continuation. So this motivated us to revisit the dimensional continuation approach to calculating the sphere free energy for other theories, in particular non-unitary theories, which have been receiving some interest in their own right recently. So we'll be focusing on the RG flow and sphere free energy with scalar cubic interactions. So yeah, concretely, we're considering a theory of n+1 conformally coupled scalar field, phi I with I for 1 to n, and the sigma, and they have Owen symmetric cubic interactions with coefficients G1 and G2. Classically, this is conformally invariant in 6 dimensions. But in less than 6 dimensions, these interactions trigger an RG flow to a non-trivial IRC of T. And there are real fixed points of this RG flow for sufficiently large n. But also for n less than or equal to 1, there are purely imaginary fixed points that describe universality classes that correspond to continuing some of these non-unitary minimal models above 2 dimensions. So for example, as we heard from Zemo and Andre's talks, the n=0 case in 2 dimensions corresponds to the Yang-Lee model, or the M25 minimal model. And the n=1 case corresponds to this M38 minimal model. And the fixed point that corresponds to this theory is the one where G2 and G1 are related in a particular way. You can also find a fixed point where G2 and G1 are equal, but that just corresponds to 2 copies of Yang-Lee. So yes, there's been recent interest in these RG flows and their Ginsburg-Landau description. And also, as we saw in Yuan's talk, there's been recent results on the 3D Yang-Lee from the fuzzy sphere. So yeah, I'll be talking about these particular cases more later in the talk. And we'll also note that there's another interesting case of n=-2, which corresponds to an SP2 theory. That has a OSP12 symmetric fixed point. It's a theory of 1 commuting and 2 anti-commuting scalar fields. And it's been studied also recently by Igor and Narablansky, and back in 2015 by these same group of authors. So we'll be focusing on these 3 cases of interest, but we can also do calculations for general n, which is what we did in the paper. So the outline for the rest of the talk is that I'll go through 2 methods for calculating the sphere free energy for these cubic scalar theories. The first is the usual dimensional continuation with d=6 minus epsilon, and we'll work to order epsilon squared at the fixed point. So this was actually computed by Grisha in 2016, who presented the results for large n, but he assumed, so since we're on the sphere, we can have curvature coupling terms. And in that work, these curvature coupling terms were assumed to not contribute to the sphere free energy of this order. But it wasn't actually computed, so we had to actually compute that, the renormalization, and we confirmed that they don't contribute to this order. And then we also used a long-range approach where we instead considered conformal perturbation theory of a bilocal action. So this is working in a fixed integer dimension with a relevant perturbation by an operator of dimension d minus curly epsilon. So I tried to keep the regular epsilons and the curly epsilons separate to correspond to the 2 approaches. Okay, and then here we also work to order epsilon squared at the fixed point. And then I'll present a numerical comparison of these methods for our 3 non-unitary cases of interest, and then some analogous results just in the usual quartic theory. Okay, so yeah, and as everyone's familiar, dimensional continuation, we need to consider all possible nearly marginal interactions and curvature couplings that are allowed by symmetry. So here is our general action. The first line is just the usual kinetic terms, conformal coupling, and our interactions. And the second line, we've separated out these other coefficients from the conformal coupling, and we've included these other curvature couplings that are allowed, kappa and b. So the renormalization of G1 and G2 is the same as in flat space. And it was computed in 3, 4, and 5 loops in these papers. And the renormalization of eta, these etas and kappa can be determined from finiteness of the 1 and 2 point functions of sigma and phi. So we carefully computed that and found differences actually at subleading order from previous calculations that have been done in the n=0 case by these old papers in the 80s. But our results are consistent with some more recent papers that have been considering the curvature couplings. So once we've taken care of the renormalization of the G's, etas, and kappa, the finiteness of the renormalized free energy is the renormalization condition for B, which we so use that to finally fix B. Okay, good. So computing the renormalized sphere free energy, we can consider the perturbative, it's perturbative expansion to order epsilon squared at the fixed point. So first we compute the Bayer contribution from the 3-point interactions in connected correlation functions, as usual. And these calculations, some of them can be done analytically, but we also use the help of this Mellon-Barnes integral package MB.M. It's made by the Smirnovs and Belitsky. And that was very, very helpful. So once we've computed all the diagrams, we express the Bayer couplings in terms of renormalized couplings. And at this stage, the free energy is still divergent. There's one divergent contribution from just the regular divergence of the free energy from the free theory. And then there's also this divergence at order G6 over epsilon. So G is going to be order square root epsilon at the fixed point. So this thing will contribute at order epsilon squared. And to renormalize it at this order, we need to, we can use this coefficient B and curvature counterterm B. So then this fixes the renormalization of B at this order. And we use that to compute the sphere free energy. So we also, carefully checked that these eta 1, eta 2, and kappa couplings don't contribute to this order. Yes. Which ones? They're not 0, but they are not, like, we think there will be contributions at higher orders. Like they have a beta function, but it just doesn't contribute to this order in the free energy. Yeah. I'm happy to talk more about the actual calculations later. Yeah. So, and then, these old results from the 80s actually would have given a result that contributed. So it would be nice to have some other other way to compute this and check that we're correct. But of course, we try to do this very carefully. So, good. This is the dimensional simulation approach. I don't know how I'm doing on time, but we'll keep going to the, So in the long, 15 minutes, okay, great. So the long range approach is, we use this other approach, the long range approach, where we consider a long range kinetic term, and then we consider perturbing it by a slightly relevant operator of dimension d minus epsilon. So here is our long range action for the cubic scalar theory. There's some normalization. And then we want our perturbation to be dimension d minus epsilon. So we take the dimension of phi and sigma to be d minus epsilon over 3. And with the thing that will set the dimension of phi and sigma to be d minus epsilon over 3 is taking this choice S to be d plus 2 epsilon over 3. So again, in this model, the renormalization of G1 and G2 is the same as in flat space. And we can just compute it up. All we needed to do for order curly epsilon squared at the fixed point was to compute this at one loop. There's no wave function renormalization in the long range model, so this is a simple calculation. But you also need to worry about curvature counterterms again. Of course, in even dimensions, the curvature counterterms, as we reviewed, don't affect the coefficient of log r. There is a possible sigma r term in 3 dimensions, but we checked again that it doesn't contribute to the free energy of a long range model at order epsilon squared. Okay, so actually computing this is the same. We do the same recipe. We can define this long range free energy as the log of the long range partition function to order epsilon squared. And we compute these connected correlators. Again, we compute the diagrams and express the Bayer couplings in terms of renormalized couplings. Again, there's no contribution from curvature counterterms of this order. And we can define this quantity F tilde long range in fixed integer dimensions as the coefficient, in even dimensions as the coefficient of a log R term, and in odd dimensions is just this order 1 term. And I'm going to emphasize again, this is only defined in fixed integer dimensions, but we defined it so that it matches the normalization from dimensional continuation, and we can directly compare these methods. And so we can express our results for this long range F tilde, sum of the free F tilde in the long range model, plus this delta F tilde, which comes from computing the G2 and G4 contributions, where this F tilde for the free scalar in the long range theory is just a functional determinant of this inverse d xy. Okay, so the way we compare our results from the long range approach to the short range approach is by assuming that as epsilon approaches a certain value, epsilon star, there's a crossover from a long range to short range fixed points. And this was studied in the Portic case by these authors. And we define this crossover value by where the conformal dimensions of the fields are equal. So the dimension of sigma in a long range model, which is d minus epsilon over 3, should be equal to the dimension of sigma, for example, in the n equals 0. This is the n equals 0 case in the short range model. And we can, we can determine epsilon star using numerical results for the short range dimension. Okay, so we also assume that the free energy of the long range model goes smoothly to that of the short range value at epsilon star. So assuming that, we can define this long range approach FLRA, free energy, by evaluating the long range energy at this crossover point. And then in integer dimensions, the long range approach and the dimensional continuation approach can be compared directly. So now I'll just present some results for the n equals 0 case. So here we start from the exact value in 6 dimensions, and we're plotting the 1-2 per day approximate for the dimensional continuation in blue. The long range approach here uses the values of dimensions from this bootstrap results. And so one comment is that the exact value in 2 dimensions is this negative 22 over 5. So it's going to be somehow getting very negative as we're supposed to be going to 2 dimensions. We actually found that we couldn't impose this as a boundary condition in the PDE because the PDE's always had poles when we tried to do a 2-sided PDE. So yeah, we couldn't really get near this negative value in the dimensional continuation case, but in the long range approach, maybe it seems to be, going more negative, but this is very qualitative. But the long range approach does agree well with dimensional continuation closer to 6 dimensions. Okay. For the n equals 1 theory, we can do the same thing. We're again using the 1-2 per day approximate. But a comment is that in long range approach, we did not find this fixed point G2 star is 6/5 G1 star, which corresponds to the M38 universality class. We only found the one with G2 stars equal to G1 star, which corresponds to the 2 copies of Yang Li. And yeah, so that's just a comment. So these are, if looking at the free energy, we can talk about non-unitary RG flow in higher dimensions between the higher dimensional continuations of these minimal models that Zemo and Andre discussed. So in 2 dimensions, this RG flow between M310 and M38 has been studied recently, as was described by Zemo and Andre. So M310 describes a pair of 2 Yang Li models. And we can just look at the flow in higher dimensions between these fixed points corresponding to the non-unitary theories in 2 dimensions, and we find that it violates the generalized F theorem, which it's a non-unitary theory, so we don't expect the generalized F theorem to hold. In 2 dimensions, as was mentioned in previous talks, the C theorem is also violated, but there is this C effective theorem, which is for non-unitary PT symmetric flows that was also discussed before, which is obeyed. So a really interesting question is whether there's any higher dimensional analogs of the C effective theorem. But yeah, I don't have any really substantive comments along those lines right now. So. Okay, so those are the two cases that have been mentioned in previous talks. There's also this additional interesting model with n equals -2. Let's see, I guess I have more discussion here. So yeah, this n equals -2 case corresponds to an SP2 model, and it has a fixed point with an enhanced global symmetry of OSP12. The beta functions for the SP2 theory you can get them from the ON theory by the replacement n is -2 and specializing to a particular relation between the couplings. And this theory involves a commuting scalar and anti-commuting scalar with the same dimension. So here we used, again, the 1-2 Pade approximant, this short range dimension from Monte Carlo. And again, here, the free energy is approaching a much more negative value. We expect it should be going to a much more negative value in 2 dimensions, which really isn't captured at all by dimensional continuation, but could potentially be captured a little bit better by the long range approach. Okay, so just very briefly, you can do the same thing in the usual quartic theory. And here we see that the long range approach agrees very well in 3 dimensions and a little less well in 2 dimensions. Yeah, and here we have a fuzzy sphere result, which would be great to have on the other plots as well for the Yang-Lee model. So yeah, and so I think I'm doing okay on time. I'll do my summary. So we performed this analytic approximation of the sphere free energy and use cubic scalar theories for general n using dimensional continuation and this long range approach, both to order epsilon squared in the corresponding parameter. And in dimensional continuation, we need to do a careful new computation of these curvature coupling or normalization, which had some differences from the previous literature. And so we also studied these particular non-unitary models of interest and found that they agree close to 6 dimensions, and the long range approach may perform better in some cases, although this is very qualitative. Okay, and we also, presented it just for a sanity check for quartic theories. So I think one really interesting future direction would be to compare this with the fuzzy sphere calculation, again, potentially for 3 dimensions where we have to extrapolate a long way from 6 dimensions, but it'd be also interesting if we could do a higher dimensional fuzzy sphere comparison with the 5-dimensional Euclidean result. So I'll stop here and I'm happy to take questions. Yeah.
By the sphere, you're putting a theory on S2 times R.
Yeah.
So how do you extract the Euclidean sphere free energy?
With this entanglement entropy connection across the 2D sphere. Yeah, and so this was done for the Ising model, and it agreed very well with the dimensional continuation result. But they're continuing from four to 3 dimensions, so it's a lot closer. And so here it'd be nice if we had. So you can of course continue down from 6 to 3 dimensions and do it. So there has been a 3-dimensional, fuzzy sphere calculation for the Yang-Lee.
It's actually not fuzzy.
Oh, okay.
Yeah. Solid calculation. That's it.
Okay, well, 2 plus 1D, yeah.
Yeah. 2 plus 1D is fuzzy.
Yeah, but if there was some higher dimensional, like a 4 plus 1D fuzzy sphere, then we could compare it in 5 dimensions. That's a bigger step to generalize it, so.
So you need from fuzzy sphere not just the spectrum, but you somehow also need to compute the entanglement entropy.
Yeah.
That is possible because you get the whole wave function there.
Yes, I guess I'm not an expert on that, on the fuzzy sphere calculation of that, but yeah. Yeah.
You maybe so for this long range approach, you get values for only integer dimensions, or it's possible to get results for all dimensions.
You have to be in a fixed dimension. I guess it's possible to consider a fixed non-integer dimension, but we're interested in integer dimensions here. Yeah,
But I don't know the dimensions. Well, no need for dimensions.
right, okay, so you need to be able to, so right, we needed to use this crossover point where the long range approach would correspond to some short range values, and we don't have like Monte Carlo or Bootstrap results and we were using like results from integer dimensions
or long range. Or
to find the crossover point. Yeah, we need to like have some value to compare to, yeah.
Can you not do that and look at?
So if there was some other short range, yeah, when there's short range approach. Right, so I guess you can of course use the short range approach. Values from an approximate method,
Yeah.
like, but here we wanted to use it from a more numerical result, yeah.
I have a question, which was, so you do these Pade approximations, but you kind of slightly arbitrarily remove the sign factor from the front. Are the results you get for the analytic continuation, so for the Pade approximation, are they robust to changing the f of d in front of your f tilde?
I think so, yeah, I know, yeah, I know in the Cordic case, they, it helps to like remove that factor, but yeah, I didn't actually check that, but yeah,
I have no idea, so.
we can talk about it also, yeah, so off the top of my head, I'm not sure, but yeah.
Okay, if there are no more questions, let's stop here.